All right, tonight we're going to be looking at and kind of introducing what Swerve Drive is and kind of how the parts of it work mechanically and how we're able to um, use it. Well, first we're going to start with a little bit of history and kind of explain just what in general Swerve is. So Swerve is one of our drivetrains. It allows the robot to move around the field. It also includes kind of the frame and things. These are what kind of the standard drivetrains look like, which we went over a couple weeks ago when we talked about different subsystems. But we did briefly touch on that Swerve exists in that presentation, and it's definitely the most advanced drivetrain, or one of the most advanced drivetrains. It takes more motors, so you need 8 motors because we're independently steering each wheel and driving it. So this allows for a lot more control of the robot. Allows the robot to do maneuvers that a normal tank drive or skid steer robot can't do. Um, so it allows for the full moving forward, reverse, left, right, spinning all at the same time, which has some big advantages in some of the games where we're able to easily realign, readjust, and change our motion of the robot as we're going a lot easier. But it does take some specific design things where like you have the corners of the robot all taken up, um, and again more complexity with the different motors and things. So like trying to figure out how this actually works and how we get to the steering is a lot of what we're going to look at today. But first we're going to look at the history. So going all the way back to the 2000 games, this is even before I was in FRC. We have this robot here that was built by Team 47, which their name was Chief Delphi. That's where the form gets its name that we use. They had independently driven front wheels, so they could steer these front wheels and then they could power them. But then the back wheels were unpowered and just castered because back then we had a lot of motor limits. You didn't have a lot of motors to be able to do anything. But this allowed them to get some motion that they needed to for the game. This is one of the first instances of this concept of kind of independently steered wheels coming into FRC. From there, a bunch more teams started playing with it, and several more teams started playing with it and doing different things. The next one we're going to talk about was one of the first robots that I saw that I was just like in wow of. So this was 2003. This was my freshman year of high school, and this robot was made by Team 111 Wild Stang. And they won the world championship that year. The game is rather simple. There were these like stacks of totes on this big ramp, and what the game ended up being was just a giant game of King of the Hill. There was a large platform that you had to be on at the end of the match, and you got some points. And depending on where the bins were, you got other points. And if you stacked them, you got even more points. But it was so easy to knock over stacks that the stacking game ended up not being that big of a component for a lot of matches. So briefly, we can see what this oh, so this is not. So yeah, so this is the demo. So you can see they had a really advanced software. They could like hit it during. This is all autonomous, so it's doing this and able to slide sideways and drive in different configurations. Um, let's see. So this is the actual match here. Ooh, if I can pull it up. All right. So So yeah, so that Wild Stang, that's all autonomous. So this was pre-programmed. This is actually the first year autonomous ever existed. So this Wild Stang robot's even more incredible. Like what they did in autonomous this season was beyond like almost what most teams are doing now in autonomous. Um, they had a ton of pre-programmed paths and things that they could do. It was just a lot. The filming back in 2003 was not the greatest. So you can already see them. So yeah, so they're just moving all of these bins down onto the field, and then towards the end of the match, they're going to. Let me get up there. So yeah, um, so the wheels, so the wheels are, yeah, you control them all through the control system, which we'll get into more when we do the control system part of Swerve. Um, but yeah, you do have to make sure that the controls and everything on all of the wheels are acting correctly, so you do drive in the correct direction. You're not like trying to scrape one of the wheels across the floor or anything, and it all works correctly. So yeah, so this is the big battle that's basically King of the Hill at the end of these matches. They were allowed to basically have these big wedges back then. You didn't have bumpers, and they're just kind of shoving robots out of the way, and they're figuring out how to stay up there. Um, So this was the Einstein Field. So this was the finals, and they do go on to win the world championship. But yeah, it's a lot of. It was a very intense robot, but not a lot of robots were able to do that even after them. A couple of years later, we have 2005. Team Hot built a three-wheeled swerve. So instead of a fourth wheel in the corner, they had three wheels. They took advantage of some other kind of weird rules at the time to allow the robot to do what's called flop. So at the beginning of the match, it actually starts vertical, and then it drives and like falls down. So this is something you can't do anymore. We have bumpers and things in place that don't allow us to do these things. But so yeah, the flop bot allowed them to change the dimensions. So they had this much bigger base, so they were much more stable. Because instead of being limited to whatever the normal footprint and the height was, they were limited to like the entire height as their base, as their length of their robot. So they were able to do some of the different controls and things to be able to slide sideways, but they didn't do it that much. A lot of it was just steering. But it was a independently steered kind of robot as well, and they did win the world championship as well with that design. So as we move into modern Swerve, we're going to look at the Swerve drives that we'll actually be using in 22 in this next coming season. So assuming the game does allow us to have Swerve, or it incentivizes us to have Swerve, not necessarily allow. You can always do it, but assuming it makes sense, there's not a game with like a bunch of obstacles we have to drive over, something like that, where it's going to be a relatively flat floor, and there's ways to there's going to be an advantage to doing Swerve. So that Swerve module that we'd be using is most likely going to be the SDS Mark IV. So SDS is Swerve Drive Specialties. It's a company run by a mentor from Team 2910. So the original design was run on their robots. And then he decided to spin that design into a company and start manufacturing the parts all at his in his garage. So he has all of the CNC equipment and everything to make all these parts at his home, and then he makes them and ships them off to teams. And this is the fourth version that just came out this summer. So it just started shipping in August. We actually haven't even built one of these yet. We own 4 of the kits. We haven't actually assembled them yet. So we have version 3 on our Swerve robot in 2021 on the 8515 robot, Gamma Ray from this summer, and then we have another test chassis that has the Swerve, the Mark IIIs on it. So then for Mark IVs, largely all the design we're going to talk about are very similar. There's just a few minor tweaks they made to make it better. And so we're going to look at the Mark IVs. That's the one we're going to use in the competition next time. But if you end up looking at a Mark III, you'll notice there are a few differences, and we'll kind of talk about them as I go through. There is a full assembly guide, so he does a really good job of walking through exactly how these modules are all built. So we have step-by-step instructions for the parts that we get on how to build them. And we'll look at this a few other times to kind of show some of the details in here that we're going to look at. And then we can buy individual parts sometimes for these. So there's a lot of different, there's some different options to configure different speeds and things you can do on there. And there's a full assembly video too that walks through the full assembly of the entire module all the way through. So there's a lot of good instructions, so it's relatively easy to build these. And you don't really have to know how all the parts work. So that's one of the reasons why we're doing this presentation, is so we can talk about what all the parts do. And we're going to be using this one as an example, but ideally most of the parts are going to be similar across all of the Swerve drives. There's going to be some unique things. This is definitely has a couple very unique things that other ones don't, but largely the principles are going to be the same. So this is kind of the list we're going to look at of the different parts that go into making the Swerve drive actually function. So the first thing that we've already talked about is that the Swerve needs 2 motors. So on almost every Swerve, the 2 motors are split. So one of the motors is your drive motor. So anytime that this motor is spinning, it's connected to the wheel and it's having the wheel spin. And we'll talk about exactly how it gets connected as we go through. And the second motor is just there to do the steering. So it's connected to the steering, and it's what actually spins or rotates the wheel itself around like this center axis. So it's how we can direct the wheel into all the different directions. So when we want the robot to slide sideways or spin while driving, it's the combination of these two motors that determine where each individual wheel is pushing. Is it pushing to the left, to the right, whatever? So depending on whether this is going forward or backwards, or if this is steering at the same time, we get different motion from the robot. Some things to know is that for some swerve modules, you can make this motor less powerful, since the steering motor isn't the one that's actually like moving your robot. It just has to steer the wheel. There are some designs that use a smaller or lighter or less powerful motor here. The SDS modules end up just using the same Falcon 500. So we use Falcons for most things. The Gamma Ray that we built this summer had Falcons for every single motor on the robot. You can also use any of the other motors that, or a lot of the other motors can fit. In this particular module, Neos and Falcons are the only ones that work for some reasons. But there are other modules where you could use other motors. There's some teams who design their own swerve, and there's no reason why you have to just use Falcons, but it just simplifies some things with the mounting plate, and it allows us to know that we're using the same motor, so it makes programming and stuff easier. And overall, it's just a little bit simpler for us to keep everything the same. So the kind of heart and what allows this whole swerve module to work is the swerve bearing. So there's in each of the modules down here, it's basically almost like embedded in this plate. We have the CAD for it here that we can see. So this is the swerve bearing, and so this is what allows the entire module to be able to spin this wheel while all of this plate stays attached to the robot frame, right? So we have these bolt holes. These are what's going to attach to the frame. And so this bearing, just like any of the bearings that we talked about before, has this inner race. So this is the part that's spinning with the module itself, and has this outer race, and this is the part that is staying stationary. And you can see these like bolts are basically like clamping it in here. So this is how it gets mounted. And so the entire weight of the robot, right, since we have these four wheels, these are the only things touching the ground. We don't have anything else touching the ground. The entire weight of the robot is being pushed up through this bearing and almost trying to like push this inner race away from this, right? So if you had a bearing that was too weak, you could imagine this whole thing could like break, and then this plate would try to go to the ground. This thing would try to go up, and it wouldn't work very well. Or the whole thing could, like, if you had a bearing that wasn't designed right, it could bind. If you had too much force going through it and you had too much friction, when you tried to spin it, it wouldn't be able to spin. So those bearings and their design have to be really important. So we actually use a specific type of bearing called an X contact bearing. And so the photo over here on the right can kind of show you the difference between a normal bearing, like this one at the top, which is just a radial bearing. So the way the balls that are spinning inside here, so this like empty cavity would have a steel ball bearing in it, just a steel sphere. And on the radial bearing, you just have like load being pushed from the two sides. So if we had this on a normal drivetrain, it would be kind of turned the other way because we'd have a shaft spinning horizontally through it, and we'd have the force going up and down supporting the robot, and everything works fine. And we try not to ever push like up and down on this type of bearing, where when we have this X contact bearing, because we have like these flats kind of milled into the races, they support both going, they support it a lot more going up and down, and don't let the bearing break, and still let it roll even when it has that other force pushing up and down on it. And so these bearings are really big. These bearings also end up being pretty expensive. So there's different modules. You try to figure out how to get them from overseas to make them a little cheaper. But they're definitely not as cheap as our normal bearing. So like the bearing for this module is a $40 bearing. So if we break these or if we mess them up, they're not the most expensive things that we could buy, but they definitely aren't cheap. Where our normal little half-inch hex bearing, those are $4 or $5 a piece. Where this one's a lot more expensive. The portion of the bearing, or the portion of the robot that actually does the steering on this version, on this module, is the main pulley. So this is orange thing right here. So this is a big timing belt pulley. that has a lot of features built into it. So it's actually a really cool part. So if I bring this up in CAD, we can see what it looks like. So this part is really, really cool. So there's a bunch of very specific holes milled into it. All of this material is pocketed. So this whole thing starts as just a big block of aluminum, and it gets through multiple operations on a CNC mill where they're just removing all that aluminum to get to the shape we want. And so some of these are really unique shapes. So you have like this tooth profile where it's missing this tooth. So you actually have you only have a tooth every other tooth around this pulley. And that still works with the belt because the belt has the pulley's big enough so that the belt's not going to skip teeth or anything, even though it's missing them in here. But this allows him to actually do the machining. If he didn't have the missing tooth, the tool he uses wouldn't actually be able to cut the teeth properly. And then the rest of the mounting holes, we'll talk about what they're all for, but it basically allows all the power transmission to happen, to actually get the drive motor to actually send power down to the wheel. And it lets us have an actual mounting places for the rest of the module. And so all of that is built into this really cool part that we can see. Where's one? So there's one here. Yeah, so it's another like $40 part. We can kind of see what it actually looks like in real life. These are very, very cool pieces of, these are parts like this are reasons why we don't make our own swerve. For us to make this part would be very difficult with the equipment we have. So it's easier to just buy the COTS assembly because this has been tested. We know it works. It's easy to get spares. We don't have to try to like make spares if we break one. We can just order another one. So it's very convenient. Okay. The steering shaft is how we actually go about turning that big swerve module. So this shaft is another pretty complicated part. You can imagine if we tried to make this, that would not be easy either. There are steering shafts on this website too, I believe. Let's see. Yeah, so the steering shaft is here. Oh, it doesn't have a real picture of it. That's not as helpful. So the steering shaft is what takes the power from the steering motor. So we have the gear that's on the end of the steering motor, which, if you remember from last week, is called a pinion when we have a gear on the end of the motor. And it has to be really close to this other gear, but it doesn't actually touch, right? So it's not driving any power to this gear. It's just driving power to the gear right here. This gear is mounted on this shaft, so that's what that little bit of the hex portion of this shaft is for. So you have this gear on there, and then it's built in. It has this pulley down here. So then when this motor turns, it spins the entire module, and it's geared down enough that it has enough force to be able to spin that module easily and not be too hard on the motor or take too much energy for the motor to actually be able to spin the module around, since it is having to like kind of drag portions of this wheel around against the carpet. But it has more than enough power to do that. Another reason why we have the Falcon motors doing our steering is we have a lot of power, and it lets it turn without any issues. So that's another unique part that we have to make sure that's much easier to have produced for us than for us to make. And then the really unique part of this specific module that we'll look at a couple of the other modules very briefly at the end, you'll see that they definitely look a little different, is we have this center gear and column in this specific module. So this center gear is actually one part in the MK3 and 4. So these are similar to the ones that we used before. So if I isolate, we can see. So this is a single piece. This is a single piece of steel that has the two gears fully attached to it. So these can't spin anytime this one's spinning too. So it doesn't have to like be mounted to a center shaft or anything. And then they have the bores in here for specific bearings. We can kind of see how that looks in the assembly guide right here. This is a cutaway view, so this is like looking at it halfway through, and we have these bearings that get pushed into the center gear, and then we have this center column that gets slid all the way through, and that center column is what the actual center gears here are going to spin on. So that center gear is going to rotate with the pulley, so it's rotating with like how fast the wheel is pivoting, and then this gear here is actually rotating way faster because it's spinning with the drive motor. So it's spinning really, really fast, so that it can spin at the rate that the wheel's going to actually turn to make our robot go. So this is this kind of like setup here where we have a single shaft and then we have bearings and another kind of shaft around it. It's called coaxial because they share an axis of rotation, but they're not going to share the same speed. So this shaft on the inside is going to be spinning a lot slower than these gears are on the outside. And that's a really important part of this module. If you didn't have that, we wouldn't be able to do we wouldn't be able to control this swerve nearly as well, because this shaft up here, when we get to, is how we get the encoder value, so we actually know where the wheel's pointing. So if we didn't have this shaft kind of sticking up through the middle, we wouldn't know where the wheel's pointing in the software, and we wouldn't be able to control the module nearly as well. These center gears are things that you can customize. So you can customize like the speed from these gears to change your output speed. So if we wanted to make the robot drive, like have a higher top speed or have more pushing power, you could change these gears one way or the other to kind of trade speed for pushing power, and that helps kind of make a decision on how you want the robot to be able to drive and handle and those types of things. This again is another pretty complicated part that we would not want to make ourselves in our shop. The kind of next stage of the gearing, so the first stage of gearing is from the drive motor's pinion to this top part of the double gear, and then we get rotation down to this middle or the lower part of the double gear, and it drives this gear that's attached to the intermediate shaft. So the intermediate shaft is located here, so you can kind of see it in a couple different spots. So it has this gear here, and then the lower portion is down here. And so we can see it in the CAD as well. So here's the intermediate shaft. So it has a little bit of a hex up top, and then it has a hex on the bottom, and has this middle portion that allows it to spin through some bearings here, and then it has spins through bearings at the bottom as well. So right on that round portion. And so this is what actually transfers the drive motor power from above the wheel, so on like the stationary part of the wheel. So this motor doesn't move at all, right? So this motor is always just driving this gear, and this motor is never going to move in relation to the rest of the robot. But this main orange pulley is, so it's going to be spinning around. And so while it spins, this gear is able to kind of spin around this central column and still stay attached to this lower gear. And that's what lets us keep power driving to this wheel while it's rotating around, which is definitely a little weird to realize that it's able to work that way. I definitely recommend at some point coming to the lab and asking for one of the Swerve modules. You can get it in your hand and you can kind of see exactly how the gears are all interacting, because it is tricky to see virtually. But you can see that this gear would be able to spin around and at some point be over on this side while still accepting power from the drive motor and still sending that power down into these red gears, which we're going to talk about next. So that's the intermediate shaft, and then that's the second stage of gearing. So we go from pinion to the large gear, and then we have another set of gearing. This is actually going the other way, so this is actually speeding up, but it just, because of all the sizes and everything had to work out, speeding up here makes sense. So this gear is actually spinning a little bit faster in terms of like revolutions per minute than this whole center gear stage is. And then, I did this slightly out of order, I feel like. Bevel gear makes more sense. We're going to do bevel gear, then we'll do forks. So the bevel gear is the sort of last part of our gear transmission. So we have these kind of unique gears that we may not have seen before. I don't think we've gone over in any of our trainings yet. So these are bevel gears, and they are specifically designed to let you transfer power and change its axis. So since this is rotating across a vertical axis, up and down, we then have these two bevel gears that move the axis 90 degrees So now we get the rotation we actually want, which is on an axis parallel to the floor, so the wheel can actually spin. So that's how we're able to have this vertical motor that has its axis spinning this way, kind of vertically, and then we can transfer it with bevel gears to a horizontal axis that lets our wheel actually drive our robot around. We don't do this too often in other parts of the robot. There are times where we may need to. We were looking at using it last year on one of our like color wheel designs, our color wheel mechanisms, the control panel, but we ended up not actually implementing it. But there are some times where you want to do this. This is actually the same way that a lot of the some of our tools, we have like 90-degree adapters or 90-degree close quarter drill. Those most of the time use a bevel gear or another type of gear that's similar. That lets us change that axis. So it's a really cool part, and definitely a unique part that definitely is a specialty part, and that kind of changes a lot of the modules depending on which bevel gears you can use and how you can package them all inside of here. In this case, with the Swerve module, the Mark IV, this is one of the big changes that happened between the Mark III and the Mark IV was this bevel gear actually got a little bit smaller so that it could fit inside of this wheel. So that we could get a wider wheel, and we'll talk about that in just a second. So going back up, we have the actual forks, and so these are another really important part of the Swerve module because these have to be very strong. Because you can imagine if these were thinner or weaker, if the robot got pushed while this was turning sideways, these forks might bend, and you wouldn't want your wheel to end up being at an angle somehow or to break off. So these forks have to take a lot of force, especially if this robot has to drive over any sort of bumps or anything. The forks are taking a lot of that impact. And so they're here in this light pinkish, light purple color. And they are actually clamping this bearing. So this is how the whole module doesn't come apart. So if we didn't have these forks attached here, this whole bearing and things it wouldn't actually work very well if you didn't have this actually doing the clamping and grabbing this inner race. So all of the parts that are spinning are able to secure it in place so this can't move around, and you can't just like pull up the you can't pull the whole module like straight up or anything. Because it gets stopped by this little bit of contact right here on the inner race of the bearing. This module is a little bit weird in that the two forks are very different. So we have the fork that doesn't have the bevel gear in it. It bolts in from the bottom, so it screws up and mounts into here. So there's threads in this pulley, and this bolts in from the bottom, where this fork that has the bevel gear on this side, it bolts in from the top. So it can be a little tricky. We definitely had some issues with this at Texas Cup on the Swerve we were using. We didn't have some Loctite in places, so we were getting some loose bolts. And so making sure we could actually get to these bolts and access them is definitely a little bit more complicated because these are on top compared to just being able to do it from the underside of the robot. The forks are they have to be held together through the shaft that goes through the wheel, so the shaft that the wheel is actually spinning on. In the case of the Swerve, the SDS modules, they have what's known as a dead axle assembly. So the axle itself doesn't rotate. So we use dead axles a lot. So you'll see them when we start getting into how we design intakes and how we design a bunch of other mechanisms. We really like to use dead axles. They allow for the axle to be a lot more of the structure, and actually can take a lot more of the load, and take more forces without bending and things. So we use them a lot. In this case, they use what's called a shoulder bolt. So this style of bolt, where you have kind of the bolt at the end, and then we have this nice smooth shaft running through the rest of it. And it has, right here, it has what's called a shoulder. So it gets bigger here, and this allows us to kind of screw it and tighten it right against a component. So this is going to tighten right into a flat part so that we can get this whole assembly completely tight and secure. Where if we just used a regular bolt, you wouldn't necessarily have that. You could, it might just like tighten into the thread or something, but it wouldn't actually tighten to this like flat part of the bolt itself. These are very, very strong. Shoulder bolts are made of really strong steel. A shoulder bolt of this size, we're definitely not going to bend. And so it goes all the way through the wheel module. And then in the wheel itself, we have more bearings. So we just have normal radial bearings since it's just a wheel. And these are what are actually spinning. And that shoulder bolt is staying completely still while the wheel's rotating around it. So a live axle would be if the actual shaft itself were rotating at the same speed as the wheel. And normally you'd have bearings mounted inside the forks in a configuration like that. Okay, I think we already talked a little bit about the wheels, but we can talk quickly about some of them. So they have, this is one of the upgrades on the Mark IVs is that we get a wider wheel. So instead of a 1-inch wide wheel on the Mark IIIs, which we were using before, we added another 1/2 inch of tread. So we get a little bit more of this material actually touching the ground. And that helps for a few reasons. So the main reason that people have noticed is that with a wider tread, it wears, it takes longer for it to actually wear away. So that was one of the problems we had, was we were driving really hard in matches and we were trying to push people and things, and we'd literally be ripping off some of this material. It's kind of a rubber that's attached to it. And you can kind of like rip it off and almost like shave it, and you end up getting parts of it that get really smooth and they don't work as well because they don't interlock and kind of grip into the carpet as well as the new fresh tread does. So the idea is with wider tread, it should take longer to wear away. And you do get a little bit more contact with the ground since we have a wider wheel down here. The part that's actually touching the carpet is, you have more of this area touching the carpet, which should let us grip it a little bit more since we have more of these little teeth kind of interlocking and grabbing onto the carpet. So the wider wheel should help quite a bit, and is one of the big advantages of going to the Mark IVs from the Mark III as we get this wider wheel. Yeah, rough top tread is a pretty common way to do wheels in FRC. It grips the carpet really, really well. So the wheel itself is actually aluminum, and we have replaceable tread that we just wrap around the outside. So that's what these bolts are. These bolt the replaceable tread to this inner wheel, and allows us to get really nice grippy rubber, but then still have a really strong aluminum wheel on the inside that we don't have to replace very often. Okay, so one of the more confusing things about Swerve is how do we actually know where the wheel is pointed? And so this gets complicated with some of the other modules and some modules before the Mark IIIs, was that you normally had something else either attached over somewhere along the steering, and you had to figure out exactly how it was geared, and you would end up having some error to where you might think the wheel was pointed one way, but it might be a little bit off to a different direction, and so it may not be perfect. Some of them are better than others, but with that center column that we talked about before, so the ability to have this center shaft going right through to the pulley, and being able to measure directly down through this center rotation of the entire module, so we know exactly where this pulley is spun. That means we know exactly where this wheel is pointing. And so this sensor up here is called an absolute encoder. This specific one is a CTRE CAN coder. And so this lets us measure a magnet that's actually put into that shaft. So right up here, this little section that's a little discolored, this is a magnet. And so depending on how that magnet is spun in relation to this encoder, it can tell exactly within a very, very fine window where that magnet is pointing. And from that, we can know exactly where our wheel is pointing. So at the start of the match, we can know, okay, our wheels are pointing, they're pointing kind of in different directions. Let's tell all the motors to get them all pointing straight ahead where we want them, without having to like manually set up where all the wheels are setting from the beginning, without having to manually have some sort of like homing routine, there's some modules where you'll like actually have them like touch a switch at somewhere around the rotation. There's a bunch of different things you can do to kind of accomplish the same thing. The absolute encoder is one of the easiest. It allows just kind of set in code where forward is for the robot. And so all the wheels are pointing the same way. And then from there, it just can turn them all to that exact same spot every time the robot boots up. And it makes our lives a lot easier. And because it has that unique center column, this whole setup works very, very well compared to some of the others, because you end up just with a lot fewer parts too. So instead of having to have another like gear or belt assembly or anything, we just have that center shaft going right up and allowing us to sense the rotation of the module. The Falcon motors themselves, which we'll talk about more when we do the control side on Falcons, they do have encoders inside of them. So a lot of the motors that we use now, both the Falcons and the Neos and the Neo 550s, which are three of the main motors that we use, all have encoders built in because they're called brushless motors and they need them to operate correctly. And so this gets us a lot more control over any of the mechanisms we use that have these brushless motors, because we have that built-in encoder, which means we can tell how fast the motor is spinning, we can tell how far the motor is spun without having to add any other hardware. So the only reason we need this external one is so we get that absolute rotation and we know where it is when the robot is off, and we can still know where it's pointing. As soon as the robot turns on and we know where that kind of where they started, we can use the encoder in the rotation motor to tell it to turn as many degrees as we want, and then we can use the encoder in the drive motor to tell it how fast to turn or how far to travel, which makes our autonomous a lot easier, and just control in general, so the driver can have more direct control and more consistent control with the robot. Okay, so there are a few other COT swerves that we'll probably not ever use, but they are useful to know exist. Other teams use them, so you'll see them around at events. One of the more popular ones is the West Coast Product Swerve, also known as the WCCP Swerve. They look really similar, and you really have to look at some very fine details to see the difference. Let me see if I can make this. So one of the biggest giveaways to whether it is a West Coast Product Swerve or a SDS Swerve is where that encoder is. So this will actually have that same, it'll have the same encoder housing right here, mounted to this little spot here. And you can see it's not over the center. And then the other big giveaway is that instead of having a belt and pulley like the SDS Swerve does, it has gears to do the rotation. So the SDS Swerve has this belt and pulley system to actually steer the module, and the West Coast Product Swerve has a smaller gear and a big gear here to do the steering. A lot of the other concepts are the same. You're still going to have a bevel gear. You're still going to have forks. You still have those two motors that are doing the same responsibility. This is the steering motor over here and the drive motor. So a lot of the same concepts as the one we just looked at, but just implemented just a little bit differently. The West Coast Swerve is what teams like 1323 use, and 148, and many others that I can't list off the top of my head. Another module that's existed for quite a while, so this one's actually been around, I think, before both SDS and West Coast Product Swerve were. It's called the Andy Mark Swerve and Steer. To my knowledge, fewer teams use this module, but it's definitely it has worked. I'm blanking on the team number right now, but a team has won a world title with it not too long ago, I believe in 2019. Brighton Techno Dogs. And so there definitely are ways to make this work. It has a little bit of, it definitely looks a bit different than the modules we looked at before. There's the plates and stuff are mounted a little bit different in here. We're not going to go through exactly how all of this works, but you can see a couple of different things. So it does have a live axle, so it has those bearings in the forks, and so that shaft and wheel are going to spin together. It also does the concept where it has a smaller steering motor, so it has the Falcon still here to actually do the driving of the wheel. Then it has a smaller motor to do the steering and to turn the wheel to the orientation we want. So yes, those are a couple more options that teams might use. We probably won't, but they exist. And then one of the final things we want to talk about is how we actually mount the Swerve. So in 2021, and kind of the easiest way for us to mount at least was to just have a bolt, which we don't actually have in this CAD. I thought we did. But up through these holes, we would put a long bolt that would go up through the belly pan. So the belly pan is this entire piece of wood that covers the whole bottom of the robot. And so we would have bolts that stick up through the wood, going all the way up through this 2x1 tube. And then the holes in the swerve module are already threaded, so they come, so they're acting like the nut. And then we make sure to put Loctite to secure them so these bolts don't try to come out. And we have nice long 2.5 inch or so bolts going all the way up through and basically clamping this top plate of each swerve module to the belly pan itself, and clamping it around these 2x1s. So that's how the whole frame is kind of secured in all four corners with our belly pan and the 4 swerve modules. And so this is largely the way we'll build our 2022 robot, most likely, is we'll have some lengths of 2x1, and we'll figure out what the dimensions are. So this robot was, what? So these were about 27 by, let's see, clicked the wrong thing. I want to say 24 or 25, somewhere in there. Yeah, 24. So we were 24 by 27, and so that's a pretty good size. Hopefully we can stay within there. So we liked building a smaller robot. It lets us get into smaller spaces. It's harder to like actually run into us if we have less room. It's also a lot easier to be light if you're a smaller robot. So that is how the modules actually work. You notice these are these swerve modules aren't fully detailed. These are generic swerve modules that make it easier for Onshape to load them quickly. So it saves some time. So we use those instead of this full module that has all the gears and everything, all the details of the module. So we don't need it most of the time. It's easier just to have this kind of generic module just filling up the space in our model for us. Okay, that's about all we have. So the last thing, if people want to learn more, there's a lot more information. There's a full hour that Team 694 presented with Team 1640 at one of their kind of virtual conferences that they did on Swerve Drive 101. It goes through a lot more of the history, and it goes through a lot more of how you actually do a lot of the designs and some of the different designs that exist. A couple of things I didn't get into here before we started doing this. There are teams who work on a predominantly 3D printed swerve, so there's a lot of teams who are working on how to print a lot of these same parts. So instead of making the really hard to make parts on a lathe or a mill and some other machining them out of metal, they're figuring out how to make some of these parts on a 3D printer. So you can still make really complicated geometries. You can still make really complicated things like this pulley, except you're doing it all printed. So it allows those resources to be done by a lot more teams. So there's a big trend for a lot of different people in several teams. I know 359, the Hawaiian kids, just put together a version of a 3D printed swerve. Several other teams, 3005 was working on one. There's several teams who are working on 3D printed swerve that allows them to sort of make the same thing, but just with less machining resources instead of going out and just purchasing it.